Hi dear friends, good morning to all. This is Bhusep Sononi, Assistant Professor Department of Chemistry, Gokli Education Society's Arts, Commerce and Science College, Jawar, District Palakkad. Dear friends, in the last part of the video, we discussed about the first order reaction and the characteristics of first order reaction. And we came to know that the first order reaction is the reaction which depends upon the concentration of only one reactant, and at the same time how the reaction or when the reaction follows the first order reaction definitely shows the particular characteristic, and that characteristic can be studied with the help of graphs or with the help of plots. So dear friends, in the last part we tried to discuss about the first order reaction and the characteristics of first order reaction. So dear friends, in this part of the video we are going to talk about some numericals based upon the first order reaction as well as second order reaction. So here we will proceed for the study of numerical as well as the second order reaction or the equation for the kinetics of second order reaction. So here the one numerical based upon the first order reaction is here, like here in this a substance decomposes according to the first order reaction rate law with the half-life of 1 hour, and what fraction of given sample of the substance will remain after 2 hours. So these are the things here provided, that substance decomposes according to the first order rate law having the half-life period 1 hour, and what fraction of the reactant will remain unreacted after 2 hours. So here the equation for the first order reaction is already provided here, that K is equal to 0.2.303 upon T log to the base 10 of 0 C0 upon C. C is the initial concentration, this is known, and C is the concentration of reactant left unreacted. So here we have to calculate the value of C after 2 hours. So here definitely T is 2 hours, but for the determination of C definitely we can take the C0 as either 1, that is 100, or we can take as, if it is in the fraction then we can take it as 1, but we don't know the value of K, and for the determination of K we have provided here the half-life period, and that is 1. So with the help of this half-life period, first of all we will calculate the value of K, and then we will use this value in the determination of same is the concentration of reactant left unreacted after 2 hours. So here the relationship between rate constant, first order rate constant, and the half-life is equal to K is equal to 0.693 upon T1 half. T1 half is given here 1. So here the K, first order rate constant K here 0.693, and if we can use this value in the next equation for the K for the determination of value of C after 2 hours. So here T will be 2 hours, the K that already we calculated from the half-life period, and C0 that can be taken as 1, but we can put later on this value. So by putting on this definitely it should be 0.693. Okay, 2.303 upon 2 log to the 2 is the time in hour, log of C0 upon C, and here after the we can write this equation for log of C0 upon C, that 0.693 into 2 divided by 2.303, and whatever answer that we will get here, we will take the log of this, and then this log will be removed, and we will get the C0 upon C, and that will be equal to 40. If it is in 100, definitely we can write in the percentage, but in the case of a fraction, this C can be considered as 1, and definitely it will be 40. So either it is 25% or it is, that is 0.25. So fraction remaining after 2 hours will be 0.25. It's very simple. Second numerical based upon the first order reaction is here. The first order reaction is 25% completed in 30 seconds. Calculate the specific reaction rate, means the K, half-life period means the T1 half, and time required for the completion of 75% of the reaction. So here we know the equation for first order reaction, that k is equal to 0.303 upon t log to the base 10 of c0 upon c. In the first case, we have to calculate the value of this k. But what things are provided here? Definitely 25% reaction completed means 75% is to be complete. It is unreacted. So C0 will be 100, C will be unreacted means the 75, and time here it is in 30 minutes. So time is also so we'll put all these values in this equation first. Then definitely by putting all these values of C0, C and the T, definitely we will have this equation, and you will take division of this, and then the log of that division will be equal to 0.1250, and after making the simplification we will get the value of what? We will get the value of k 0.009596 per minute. In the second case, we have asked here to calculate the half-life period, but the relationship between half-life period and the rate constant is equal to is t1 by 2 is equal to 0.693 divided by k, and this k here we calculated here, we will put these values in the instead of k, and then definitely half-life period will be 72.23 minutes. In the third case, definitely we have asked here to calculate the time required for the completion of 75% of the reaction. 75% of reaction is completed means 25 reaction is to be completed or it is unreacted. So C0 will be 100 and C will be 25. By putting all this, and already we know the value of k, and definitely we can calculate the value of this t. So we can write this equation for t by putting the value of k, C0 and then C. By making all this simplification, the time required for the completion of 75% of the reaction will be 144.50. It's very simple. So dear friends, in the last part of the video we tried to discuss about the first order reaction. Now we will proceed for the study of second order reaction. Second order reaction is a reaction whose rate is directly proportional to the concentration of two reactants, and definitely that reaction is called as the second order reaction. So rate of reaction may be proportional to the product of two same or the equal initial concentration, or these two concentration may be different or than equal. Here we will consider the initial concentration of the two reactors are equal, and in this case definitely if the initial concentrations are same, then this will be the condition. Two A reactor molecules give the product, and if the reactant molecules are having a different initial concentration, then this will be the case. A plus B gives the product. If A is the initial concentration of the reactant, that already we discussed about the first order reaction, then X is the amount of reactant means the amount of product formed in time t, then amount of reactant remaining unreacted at time t will be A minus X. So as it is the second order reaction, definitely it will have the coefficient 2. So 2 number of reactant will decide the rate of reaction. So this power will be 2 and this power indicates the order of reaction. So after removing the proportionality sign, we instead of for removing the proportionality sign, we will take the proportionality constant k, and by collecting the terms of x on one side and the terms of time t on another side, we will have this equation dx upon a minus x bracket square is equal to k into dt. So we will integrate this equation. Integration of dx upon a minus x bracket square is equal to k into integration of dt. So integration of dx upon a minus x bracket square will be this, will be 1 upon a minus x, and the integration of dt will be small t, therefore is equal to k into t plus constant of integration k prime. In order to remove this value of constant of integration, we will put the value of time and the concentration 0 at time t is equal to 0, concentration will be also 0, and definitely t will be 0, so this term will be also 0, and x will be 0, so there will be this a minus 0, so this will be only 1 upon a. So therefore k prime will be equal to 1 upon a, constant of integration will be equal to 1 upon a, and we will put this k prime here in this equation. Definitely we will get this equation 1 upon a minus x equal to k into t plus 1 upon a and we can write this equation for k into t. We will get this by transferring this on one side. On this side 1 upon a minus x minus 1 upon a. And after the making simplification of this, definitely we will have this equation that k into t is equal to 1 upon a minus x minus 1 upon a. And we want to write this equation for this k, rate constant for the second order reaction 1 upon a into t. But after making the product, that is, if we'll solve this, it will be a, then minus a minus x divided by a into a minus x. So this a will get cancelled, plus it will be plus x. So x upon a minus x, and this is a into this t. So 1 upon k is equal to 1 upon a into t into x upon a minus x, and this is the equation for the rate constant of second order reaction, and this equation is called as the integrated rate law or characteristic for the reaction of second order with equal initial concentration. So this is very important equation. K is equal to 1 upon a into t into x upon a minus x, and this is the equation for the rate constant of second order reaction with equal initial concentration. So dear friends, today in this part of the video we try to discuss about the numerical based upon the first order reaction and the kinetics or the rate equation for the kinetics of second order reaction. So dear friends, in the next part of the video we will resume to discuss about the different characteristic of the second order reaction and the numerical based upon the second order reaction. Thank you very much.